Good evening.
Hello. I'm going to have a short introduction word and then I'll give the word to you. Is that okay with you?
Excellent. We are ready this side.
And I'll start. We are at approximately 170 participants, so that's looking really great. I want to call everybody welcome here in this symposium in honor of our 19th birthday of the Delftsche Studenten Aeroclub. We are going to listen to 3 speakers who are going to talk about some of the new innovations in the technology of gliding. Firstly, I want to say that we've had over 380 registrations, which is really great. So I want to thank you all for joining us this evening, and I'm really looking forward to listening to our speakers. We will probably be recording this event, so if you have any problems with that, you can email us, or you might just want to leave the symposium. There is no other, there are no other people inside except for us and the speakers, so don't worry about that. Furthermore, this is a very new program to all of us, so we're still figuring it out a bit. We've had some technical difficulties already, but I hope that everyone is managing just fine. If there are any problems, you can contact Leanne. You've had we shared her phone number. You can always ask questions in the chat. The chat is just meant for what it says, chatting. And if you have any questions towards the speakers, you can go into the Q&A, and we will, the moderators, Leanne, Toon, and I will be moderating those questions, and we will be the ones asking them. So please, when you ask a question in Q&A, make sure you send it to all the panelists and not only towards the speaker, because then you have less chance of your question being asked. Furthermore, you can see the schedule over here. We will start with Uys. He will give his talk, then Loek Boermans, then Gliner. Approximately all the speakers will have 30 minutes of talking. We are expecting them all to run a bit out, but that's fine. And then we will have 15 minutes of questions, which like I said, we will be the ones moderating those. I want to thank you all for joining us this evening, and I want to thank the speakers in advance for coming to our symposium. We are really glad for that. And now I would like to give the words to Uys for the first presentation.
Thank you so much, Eva, and welcome to everybody. So Eva, if you can just allow me to share my screen, and then I can attempt a presentation.
You can now share your screen.
Okay. We managed to find the unmute button. Okay, first, on behalf of our design team, and the aerodynamic team is led by Dr. Johan Bosman, so I would like to present a few slides. But just a first disclaimer that I'm not an aerodynamicist, so I'm only using buzzwords, and it's easy to catch me out. So I was on a bit of a training by Dr. Uys Jonker to tell me what to say. So apologies if it's not technically all correct, but I try to understand what we are doing. So I'm going to talk tonight just about the development, with the focus mainly on the aerodynamic development, and then finally how it slowly is introduced into a product. So our development process at JS is a bit formalized nowadays. So we develop a glider as follows. We're doing some aerodynamic research, and the aerodynamic research is done separately and giving us the building blocks to develop a new product. And when we start to develop a new product, we first hear to the customer, what do they want? We try to do market research, and we send surveys out, and we try to understand what is the wish of the customers, what products is desirable. Obviously, this we have to match with the certification requirement, and the certification requirement for Sailplanes is the CS22. And when you mix these two requirements, you have a product definition. Once we have the product definition, we start with the aero design, which is based on the aerodynamic research that we have followed. And then obviously the structural design follows the detailed design. We build a prototype, and then the testing and certification starts. So to see that we are actually closing the loop to the production definition and to the certification specification. And then we set up the production line. So it's quite an intense process. It takes us at least 3 years of aerodynamic research to develop a new product. And it takes us about 2 years to develop it and another 2 years to certify it. So it's a long process, but this product runs not sequentially. So they overlap a little, and the idea is that we can develop the product every 3 years. If we are quick, we will be able to do that, but a new product might take even a bit longer. All right, so our aerodynamic research is mainly done in partnership with the Northwest University in Potchefstroom, led by Dr. Uys Jonker, and our Jonker Sailplanes team, which is led by AP Kotze, and obviously Uys Jonker is the chief design engineer looking after the structural part. So tonight we're just going to lift the curtains a bit, a few things that we are doing. So the aerodynamic research currently at the university focuses on 3 areas, and one of the areas is the CFD calibration and how we apply these new products in the design, and I'll elaborate slightly on these aspects. The second interesting thing that we are doing is to use deep neural network frameworks for sailplane design using performance models optimization. And I'll just give a quick slide on this. It's some PhD work we're doing on this, and the idea for this is that we're using the computer to do the guesswork of how our profile should look, and stop us doing the guesswork. And then obviously we're looking into suction, and this is also a topic that Dr. Boermans will address tonight, as he is quite an expert on this, but we also have done some research on selected areas to see if this is applicable and if this could improve the performance on sailplanes. Right, so just get us going to a bit of the aerodynamic research. I'll just give a quick overview, and I think a lot of you guys will be very familiar with the terms and might find it a bit boring, and for others it might be something new. So conventionally, we all use wind tunnels to develop sailplanes, and I think Delft University is one of the major players in developing new products with wind tunnels. And initially, we also used wind tunnels. Our wind tunnel that we've been using is at the University of Pretoria, but unfortunately, the turnaround times takes about 6 months. Basically, you develop a model, you insert it in this model into your wind tunnel, and then you develop you measure the flows inside this tunnel to understand what is the aerodynamic performance of your model. Unfortunately, the other method we're also using is conventional analysis methods, especially with X4, a brilliant program that is a 2D code. We're also using the KK Aero numerical panel method procedure to develop complex areas like around the fuselage wing junctions. But lately we found that the improvements on these performance areas are almost in the same order of the accuracy of the panel analysis method. So if we would like to have a 1% improvement or 2% improvement on the profile, the accuracy of these models are also around 2%. You don't really know if you will have an improvement. So we are using now some different techniques, and this is where we start with computational fluid dynamics, where we're actually using a large mesh for the flow domain. But you have to use big computers, and luckily we have access to the cluster network at the university, and they sometimes complain that we pull the complete computing ability of the university down when we run our simulations. Initially, it was about a week of time to solve some of these iterations, because it's about 8 million cells and 8 million equations that you have to solve simultaneously, and it was not possible 10 years ago, say 15 years ago. Nowadays, with the computing power available, this method is really a super method. But maybe I should just like to go one step back and to take you back in the design history and how we designed what we thought the ultimate sailplane was, which was the JS1. We look at around 15 years back on this story. So what we thought to do is we would like to model everything we're doing. So we set up mathematical models and to predict what we're going to get. And from the mathematical models, we try to predict and to design high performance sailplanes. And so far we were not very far out with our modeling, and we think that modeling saved us a lot of time. So basically, to do a sailplane that's the best, you have to optimize the cross-country speed. So we said the average cross-country speed was derived with a certain formula, and if you can optimize this formula, then you will have the optimal sailplane for cross-country. And we're using also still this method in principle. However, we're nowadays using very complex integrated methods, which taking weather models into account and thermal models, and then the sailplane models. And in the end, we see what is a typical average speed over different type of days, and what type of average thermals over what days will give you a contest win. So it's more about winning a contest than it is about designing for best L over D. Okay, so let's just go a little bit further. Once we complete the design to JS3, we managed a calculated L over D of 53, and this was actually confirmed by the Tijd Vliegt that it actually achieved this. And they had a very good sink rate, about 1.6 meters per second at 200 kilometers an hour, which we thought was a good glider. And then we thought, how do we improve on this glider? And this is where we start to look at it, and we call it the JS3 challenge. So how do we improve on a good glider like the JS1? We looked at optimization of wing profiles, and this is where we come now in with the integrated design of profiles, and not just by defining a best profile. We're looking at what is the best profile to win a competition. Obviously, we look at planforms. Elliptical planform is the best, and with elliptical lift distribution is quite the best. So we are really pushing hard to have as close as possible elliptical planforms. We always try to maximize the aspect ratio, because then obviously the induced drag is limited, but this is very much limited by the stall speed requirements and by the limited span. So if you have an 18-meter aircraft and you want to optimize the aspect ratio, you normally run into area, and then your area is not big enough. So we thought with the JS3 we'll get to the ultimate aspect ratio, and we will just manage the minimum stall speed requirements. So this is the higher wing loading when it comes in, and we've proven with the JS3 that the maximum certified wing loading is 60 kilograms per square meter, and you have to design a profile with a much higher maximum CL if you would like to go higher than this, and obviously then you will not have high speed, very good high speed performances. So with a high speed performing profile, 60 kilograms per square meter is what we think is the maximum. And then obviously a smaller fuselage. I think Symposium is quite good with a small fuselage, and therefore the JS3 was under pressure to have a little smaller cockpit, but still taking quite large pilots. And then the last thing was the reduction in the complex 3D flow areas. And this is really where CFD tools came in very, very handy. So what are these complex flow areas that we're talking about? Wing junctions, winglets, cockpit ventilation, fin fuselage junctions, control horn fairings, tip wheels. Those are the things that we could solve with CFD in a very efficient way. And we're going to just run through a quick exercise to see how it works. So we actually need a calibrated CFD tool, not just a normal CFD tool, because we need to predict the crossover from laminar to turbulent flow if we would like to take advantage of these CFD tools. And this is typically what a CFD will show you, is where these crossover points are. And this is not so easy to achieve as these tools have to be accurately calibrated. And we quickly talk about how to calibrate them, because that was one of the questions from the audience. But let's first put drag into perspective, because I think all the designers, if you would like to increase the performance of the aircraft, you really need to reduce drag. And we thought that the next generation 18-meter class glider, which we call the JS3, if we would like just to have a 2-point increase from a 54 to a 56, what is required? So let's make an example. Best light is 110 kilometers an hour for a glider of 600 kilograms at the 53 times G. It means that there's about 111 newtons of drag to achieve that 53. And if you would like to have a 55 and you just multiply this into the equation, you'll see that you need a drag reduction of 4 newtons to achieve 107. And this is what we initially aim for, to see, well, how can we save newtons of drag? Typically, that same efficiency at high speed will require much higher loss in drag, and therefore we have to have 8.6 Newton of drag if we would like to have a similar performance increase. Okay, so let's see how we address these things. We looked at CFD, and I think all of you know nowadays, especially if you're in this meeting, what is CFD, but they were not able to predict this laminar to turbulent transition areas, and it was not really suitable many years back for sailplane design. But now with new transition prediction approaches in CFD, this is actually possible. And this is what Dr. Johan Bosman in his PhD really looked into, in how to tell the software where the transition areas would be. So we all have know that CFD is basically just a numerical wind tunnel. As you put a normal aircraft in a wind tunnel or normal model, so you can put a numerical model in a 3D wind tunnel, which we call CFD, and you get very similar results. So let's just have a look at the comparisons between a CFD approach and a wind tunnel approach. In a CFD, you first, I don't know how to scroll up my presentation there. Apologies. First, you build a wind tunnel model, and this takes a few months to make it accurately. And in CFD, you just generate an accurate CAD presentation. Then you, in the wind tunnel approach, you select a wind tunnel and test section, and here you generate a flow domain with boundary conditions. And in a normal wind tunnel, you select the wind tunnel test conditions. Here you set up your flow parameters. You run the wind tunnel. Here you just press solve. Instead of running an expensive wind tunnel with lots of wind and noise, we just push a solve button. Then we analyze the data, and you also analyze the data. And you repeat this step in an iterative process until your design is good. And this is where we come just now in with our neuron network that we're busy developing, how we do this, how we're going to bypass these steps of doing it manually. Just quickly look at how we set up the model. As you have your computer model, you put it inside in a computational flow domain. So basically also have what we saw, the interface, the bottom wall, the top wall, the pressure outlet, and the velocity inlet. So it basically just looked like an actual wind tunnel. And then you run this thing. So if we just look at the transition models that we now looked at, we just talked about it, that the CFD models cannot predict the transition accurately. Why is that? Because the Navier-Stokes equations are too complex to solve numerically. So they have lots of terms behind, and these terms is actually needed to be truncated to make it solvable for computers. And because you solve it, you lose certain of the attributes of the formula, and it loses mainly the transition point, and therefore you have to actually tell it where is the transition from laminar flow to turbulent flow. I hope Dr. Bosman will just correct me if I don't say it exactly correctly, but there are certain few things how we could do it. How you do the Reynolds average, I think we're using these methods to tell the computer where that transition point will be. So the Reynolds method is proved to be feasible. And the Walters model as well was chosen for certain validations of our simulations that we have done. Okay, but you have to validate it. So once you have selected the transition model, you have to validate it to see that you are predicting the transition from laminar to turbulent flow accurately. And therefore we looked at two cases which is very well known. We first did a 2D validation, and then we did a 3D validation. So for the 2D validation, we used a very well-known profile, the NACA 653418. profile where the measured data in wind tunnels is extremely well known. And the NACA profile is quite a extensive, large laminar flow area with laminar separation bubbles on both the top and the bottom surfaces. And obviously the drag increases for larger Reynolds numbers, and tests were carried out in turbulent levels and the same conditions as experienced by airfoil in a sailplane. So we first use this and we compare the 2D model. And you can see the results that we achieved. If you look at the red results, is what X-foil is predicting, and X-foil is quite a good estimation. And this is measured by experiments in the wind tunnel, and the fluent data gave us that green model. So it was very accurately, the 2D model gave very, very accurate results compared to the 3D model. Okay, then we use a 3D case, and we were lucky enough that the München University, Aeroclub München, shared the MU-33 concept sailplanes wind tunnel test data, which was also very accurately measured. And as you could see, this was measured in the wind tunnel by München Aeroclub, and this was how our model with the transition of, if you could see, that is the transition point between the laminar and turbulent flow areas, and how accurately this was predicted by our models. So we used a few things to calibrate it, and I just would like to say that Dr. Boermans says we are continually working in processes to improve on the accuracy and the transition point optimization or of the models, of the CFD models. Here you could see how it looks in the wind tunnel. And this is also a good indication of where the transition point is sitting, and this is what the CFD model is predicting. So once you have real calibrated CFD data, you can for the first time actually use it. If you just use a normal CFD package without calibration, you will never know. You'll have beautiful pictures, but you'll never know until you fly the aircraft. And there's validation cases. You can also see the wind tunnel data compared to the fluid simulation is very accurate. And therefore, since I think it was really the last 10 years that we are just intensively doing CFD design work, and we don't use wind tunnels any longer. All right, so what did we do with this CFD tool once it was calibrated? So we looked at a few options where we can optimize it. So we first look at the position of the wing. And when we look at the position of the wing, it looked that we could have a reduction of 3 newtons just by moving the wing to the correct position. And we looked at a few baselines at the JS1, we looked at the SB14, and then we also looked at the 2 other cases to see what is the contraction required to optimize the drag. And we actually thought that the quicker contraction will be the best, but after some simulations done, we saw that case 2 was actually the best. It was not the smallest case, it was actually this model where we got the best drag reduction of about 5 newtons. So we implemented the JS3 looking more at case 2. Then we also look at cockpit ventilation. This we already implemented in the JS1. For the JS3, we had to move it to a less ideal position in the bottom of the fuselage, but the reduction according to our CFD was in the order of about 0.3 newtons. Not a lot, but it's there. Then we looked at the control horns at the rudder positions, and we also used CFD for that, and we looked at the flow, and we had a reduction of 0.4 newtons. Then we looked also at the changes in the fin area, and there we found 0.5 newtons. The other one that I did not mention was the root suction. This is one area that we technically could not work out with the buck wipers in place, so we had to select between root suction and buck wipers. But if you could see that we could actually achieve 9.8 newtons of drag for the JS3, except for that 0.6 that we could not implement. Now, if you reduce the drag with 9.8, your glide angle increases from a 53 to a 58. So we could not get to 58, but our latest test results from the EDA flick with the JS3 showed that we got to 57. So it shows that even with the data available from the EDA flick, we managed very close to what we thought is the maximum performance available in a JS3 with the current technology. So our CFD really proved the results, and thanks to the EDA flick, we could have validated these results. So now we have a nice tool that we can make nice pictures with. So this is just how we've continued to calibrate our CFD. This is the JS4's winglet already, which we doing some improvements and design work on it. You can see how high wing of the JS3 resulted in some improvement areas. And once you apply all of these techniques, you finally come to an aerodynamic design, which you now have to sell to the structural team and say, can you fit your structure into this minute little shape? And then the conflict starts, because the structure guys always would like to have more area and more volume, enclosed volume, and the aero guys would like to have less. And this is where this process could actually start all back from the beginning. If the structural guy can't fit it in, we're back to the drawing board. We're also doing some research flights. You can see here we confirm flow tests with our CFD results. You can see there's quite a nice comparison in this. You can also see there's a little bit of the influence of the probe on the fin. It's also one of the reasons why we moved the probes to the tip of the JS3. Not a massive effect, but you can see there's a little bit of a discrepancy. It results in on the edges. Okay, so this is some of the work that we've done with CFD. Now we come to a very interesting topic that we're busy with, and this is allowing the sailplane to do the guesswork instead of us fiddling with profiles. Because the normal way how we design a profile is you have a base profile, you make small changes, you run a analysis on it, and you compare it with the previous results, and then you have an idea if you're moving to an improved design or if you're moving towards a reduced design. And if it's improving the profile or if it's worse. And now if you can actually use a different method to do this guesswork, we can actually do it much quicker. So this is one of the PhD studies that we're currently busy with at the university, use deep neural network framework for sailplane cross-country performances. And I just quickly like to explain to you what we think we're going to do here. So basically we start with the seat profile and with parameter constraints. For example, the structural guy will say you cannot go thinner than this. And the wingspan cannot be longer than this if it's an 18-meter span, for example. And then we start off with the seat profile, initial profile. And here is where we allow the computer, if you use neural networks, to design the profile. Now, normally profiles are just designed using XY coordinates. So if you look at a certain section and you have those XY coordinates, you have to define quite a huge number of coordinates to define the profile accurately. So you can imagine, I would think on a normal sailplane profile, I would be uncomfortable if there's less than 2,000 coordinates defined, because it's little small straight lines, and you will not have an accurate one. I would guess about 2,000 points will be quite close. Bossy correcting me. It is only 200 points. If you have 200 points on the profile, 200 coordinate points, you can actually solve it. But what we have done, and this is part of the study that we've done, is that we're actually defining parameters to define the profiles. Instead of solving 200 points here, the airfoil parameters, if you can define parameters like, for example, the camber, the thickness of the profile, and various other parameters, and you can put this in a function, then you can solve a function with much less parameters. And we've developed now parameters where we specify only 11 variables. And if this variables is now in a function that we've developed, the profile is accurately specified. And then the airfoil program can actually analyze this function and actually doing some optimization on this 11 parameter function to determine the airfoil performance characteristics. Then we do analysis on it, we determine the airfoil performances and go all the way back and do another one here. And actually using neural networks to determine what is the new profile. So in the next couple of years, we'll be hoping that we're just specifying these two parameters and that the optimized profile will be generated. We're having extremely good feeling about this project, and I think in the near future, it will be extremely nice to see how neural networks will design the next generation airfoils. One of the other studies that we've also been doing is on suction. We've been following what Loek Boermans is doing with suction, and it's quite interesting, and we're quite excited about the work that has been done in suction, and it could actually result into major performance increases. However, the technical question is still not solved. But we looked in what areas can we actually solve it. So we selected the fin to see what is the performance scores if you actually use suction. What we did found is we found a generator for suction. In other words, you have to create a low pressure source, which we found there. And we found out that by using this, we can actually move the laminar flow area from that point to that point. And this gives a 30% reduction in drag in the fin area. which in the end will result, I would guess, to about 8% performance, maybe a little bit less, 8% drag performance on the total sailplane if we just reduce the drag area on the fin. And you also see that we have a slightly higher aspect ratio on the JS3 and JS2 designs now, just to take advantage of a larger area and a larger improvement. So these are the areas that we are currently busy with our aerodynamic research. So now I would just like to go a little bit back to where we were a bit earlier in our design process. As I said, we did aerodynamic research. I showed you how we do the aero design using a bit of CFD. I can actually say a lot of CFD, or I can almost say only CFD at this moment. And then we hand it over to the structural design guy. As I said, this guy is where the conflict starts, and he needs to first design for the fuselage, for example, a stress skin design where all the loads are transferred required inside the skin. He needs to do a little bit of structural reinforcement in the cockpit area to meet the 9G requirement. As you can see how this is developed here, this is to transfer all the areas from the fuselage into the wings. You see a couple of bulkheads for the engine. And then we run our FEM analysis on the structural analysis. So we mainly do hand calculations backed by, or shall I say, we're mainly doing FEM analysis backed by hand calculations. And then ultimately we test the structure with physical tests for certification. It's a bit easier to convince the authorities if you do an actual test than to give FEM results. And then the detailed design follows. And the detailed design consists normally out of the control system design, the aerodynamic, the economic design, and the power plant design. So if you just look at one system that I've selected, is for example the landing gear. Traditional methods would have showed you, if we just use normal methods, we're using a lot of Excel to model again. So everything we're doing is done by Excel. Even that we're using expensive software packages like NX from Siemens, we could do modeling in quite a nice way. You have much more control if you do the design on Excel. So for example, if we designed the landing gear on the JS1, we modeled it, and we're actually making graphics with a slide bar showing how the retraction and extension of a landing gear works. And then all the loads are telling you what is the hand load. So you could see how hard the landing gear would have been to retract it. But by manipulating it with a few other bell cranks, we actually designed the JS1, JS3 landing gear that by the back end of the lever, where you don't have a lot of forces, the forces drop to zero. And this makes it very comfortable to retract, even for the smaller or female pilots. And then actually this is how we've modeled it back into NX, where the CFD calculations is also confirmed, backed by the Excel calculations. Then the structural engineer needs to fit this into a complex shell. As you can see, a very small shell, and everybody's fighting for space. If you can now imagine, you have to fit in a wheel, a control system. You need to find the seat pans, the seat back, instrument panel, cockpits, and then even you have to fit in the, as we would like to call them, the idiot behind the stick. And this is, most of the problems is to create enough space for a larger pilot without compromising the aerodynamics too much. And this is where I think with the JS3 we found quite a small cockpit capable of quite big pilots. The manicure that we selected here was a 120 kilogram pilot, 2 meters tall, if I recall correctly. So we aim for 120 kilograms, 200 centimeters tall. And it seems if they are fitting in. Righto, if we look into the other structural design areas, you can see how we have to design all these bulkheads and things into it, and also the power plant. In this case, the jet one. As you all know, we're busy now with the rear electrical propulsion system, which we will start to integrate shortly. We already have tested all the platforms with it, the pure gliders, and the electrical system will be installed shortly. And you can see everything is fighting for space here. Once this is done, we move over to prototyping, where the prototyping needs to be constructed. And you can see I'm just, as this, we're running slightly out of time. I'll just quickly show you how from the model we start to design our tooling. So that is the tooling boards and the jigs for the wing molds here. You can see this is typically what a mold look like, with all the jigs to hold the parts. We have to design tools and jigs to do the integration between the wings and the fuselage. I can just say that on the latest product, our JS2, the wings were completely built separately, and the fuselage on this side without any integration, and we just push the wings in and they fit it without any interference issues. The fuselage is typically look like this, the plug that we design. And if we do it in real life, we CNC machine it out of MDF or superwood, as it's known in South Africa. And the superwood is then carefully positioned on accurate jigs. And then you start to finish this mold by hand. You can see this is the plug now prepared for the mold. And pulling the mold out of, and then a little later you have the actual mold coming out of the product. And this is what a typical mold looks like. Once you've designed a mold in all the inner sections, you spray the mold and you start the structure layup. You can see that's the skin there. You do the internal component installation and the control system. This is the mixer system in the CAD, and this is the actual one. And then you have to close the two fuselages together. You demold. It looks quite not like a lot of work, but this could take up to 6 months to do the jigging and the tooling correctly. And then you have your first fuselage, and obviously the chief design engineer who tried to fit in a 120 kilogram pilot just want to check if at least he can fit in. At least that would be at least the first prize. If the chief design engineer can fly his own aircraft, it would have been a bit disappointing if he can't fly it. As you can see, then this was the JS3, the first attempts, integration of the fin to the tailplane to the fin. Manufacturing of the wing starts here, and you can see initially we're just using some wooden tools to position the spars and the positions, and you do follow exactly the same process as you would with a fuselage. Also some tooling and jigging to position all the parts, building all the parts in the inside, and then the final moment comes, does the wing fit to the fuselage? And it's quite a stressful moment for everybody, because the design engineer knows if this doesn't fit, we're going back to the drawing board for a very, very long time. And you can see there's the first fit of the wings to the fuselage, and then suddenly it all works, and you go to the paint shop, control system installation, instrument installation, and finally, in the middle of the night normally, the first product is ready. So this is the design process just summarized in a very, very short program. This is the JS3 in the 50-meter configuration. I just want to mention this whole aircraft was built in 4 weeks. It's all we had before we went to Benalla in 2016. And after this, the testing and certification starts, which took another 2 years. And the certification base, as you all know, is a few items that you have to demonstrate to the authorities to show that your aircraft is safe. We're not going to go into that because we're running slightly out of time. But I just would like to show you, and then we start with the certification flight testing. So this is the end of our product, of my presentation. Just want to quickly show you our latest one. The JS2 test flew a couple of weeks ago. This is some of the pictures we took on the very first test flight. So you can see this is, I would say, a all designed CFD and FEM aircraft. Our first one that was designed just with modern computer tools. This is what the prototype looks like on the inside nowadays. It doesn't really look like a prototype. We would like to make the prototype look like a final product. And I think this is the result of a happy team. If you have a good engineering team working with a university doing good results, you have the ability to meet the customers' expectations. And if you listen to the voice of the customer, you end up with a happy crowd. So thank you for the time. I think, Eva, this is my presentation. I will mute myself and open for some questions.
Thank you, Uys. There were some questions already in Q&A, so I'll give. I hope Toon is here somewhere as well. He will be.
Yes, I am. Hi, I hope you can see me. Well, thank you, Uys, for your wonderful presentation. We do have some questions, and I can see coming more in already. And we like to involve the audience as well. So we would like to give the floor to Tom Whitkin, who has a question on the design process. And I hope my colleague can ask to unmute Tom at this moment.
Hi, how are you? Thanks for hosting this. Hi, I fly with the Greater Boston Soaring Club in the Northeast U.S. And my question was how you weight cross-country speed versus other factors like cockpit comfort, safety, ease of assembly, manufacturing cost, repair complexity and cost, etc.? Thanks.
John, if you can just repeat the question, it was a bit unclear to us.
Yeah, so the question was, what if you are defining your product, what do you account for weight factors for different aspects of your design? So, for instance, cockpit comfort or manufacturing, ease of manufacturing or ease of assembly or repair complexity and costs. How do you weigh those in your design process?
Okay, I don't have the list in front of me here, but we have, I think it's a 5-point criteria that we design the aircraft according to. And if I remember correctly, the first one is safety, because firstly you are restricted by the CS22, and the CS22 forces you to design a safe product. So we're looking at safety as an ultimate design constraint. If we cannot meet that one, then the design requires changes. The second one that we are looking into is actually handling. So we regard handling as a very, very high priority because it almost goes hand in hand with safety. We feel that if an aircraft even complies to the CS22, but the handling is not adequate, that it will not be a safe platform for the bigger audience. You may find it safe for 95% of the audience, but 5% will not be sufficiently. Our third aspect is performance. You might think that at JS that performance is our first aspect, but it is actually our third requirement. The fourth one that I was thinking about, I don't have the list unfortunately with me. Yeah, maintainability is the fourth one. It's maintainability, and then it is manufacturing ability, and only the last one is costs. And the one that I actually, what Bossy is pushing is aesthetics, that it looks nice. But we allow him to design it in the aerodynamic design. So you may look the gliders as beautiful as possible, meeting all of these other requirements. So we don't design to make it look good, but it automatically ends up into our design. Because if your designer has an eye for nice aerodynamic lines, it could be incorporated into a good performance package as well. So this is basically how we look at it. Pilot comfort is one of the aspects which is always in conflict with performance. It is very tempting to make a very small cockpit, and the performance results are really noticeable. In the JS3, we really tried to have a cockpit as good as one can get. So we don't want to say we have any other fuselage will have superior performance to our cockpit, but with the ability to fit that big guys. And that was a major design challenge for us. So that was actually one of the biggest design challenges. How do you fit in such a large pilot in such a small cockpit? And there's quite a few tricks. I think if you climb into the JS3, it feels to me a little bit small. I must admit, I prefer a slightly larger cockpit. But if you fit a large pilot of 120 kilograms at 2 meters, it also fits in. So it is me always amazing how these guys fit in and fit in comfortably. And it is just the way that the cockpit is laid out. So I think Ati did quite a good job using these manicures and CFD, not CFD, modeling, CAD modeling to achieve that. I'm not sure if I answered the answer correctly. In my opinion, is performance is slightly higher than pilot comfort sitting in the cockpit, but somehow most pilots are not complaining too much.
Yeah, all right.
Perfect, thanks.
Yeah, well, you can hear Tom. It's a nice answer, extensive answer as well. Well, there's still some questions coming in, and I'm afraid that we can't answer all of them. So we have a little bit more time left. So someone asked already to how much you used machine learning in your process, and yeah, you use it extensively, and that's very nice to hear. But there are also some new developments, and with regarding to new materials, and how do you think that those new materials could improve the performance of your new gliders? Are you working on that currently, or is that an ongoing process?
If I can answer it this way, the current materials that we select, we mainly design with carbon to make it as light as possible. and the carbon properties are sufficient for our existing range of products. However, we had to use carbon with higher stiffness module. How do you say it? Modulus? Stiffness modulus to reduce the twist. So for the JS5, we had to look at different materials. Otherwise, the twist that is as a result of this long, thin wings is taking all the advantages that you get with the wing away. And it is still, there are still not materials stiff enough to make the JS5 or the open class wing as stiff as we would like to have it. So we had to do an iterative process between the structural engineer and the aerodynamic engineer, and we had about 5 iterations to change it from the optimal aerodynamic design onto what the practical one is, where we will not be limited, our performance will be negatively affected by the resulting twist. So if there's a bit more better materials, it will definitely help a little bit for the open class. For the smaller, for 18 up to 18 meter, it will have very little impact at this moment, according to me. You don't need better materials up to 18 meter.
All right, thank you. Thank you for your clear answer. I would give the floor now to Eva, who also wants to pose a question from the audience.
So you mentioned how you want planes to be as small as possible, but Joris asks, he first thanks you for your explanation, but he asks, when we can pre-order and enjoy these designs effort in a 2-seater, are there any plans for a 2-seater in your company?
We have always a lot of plans, but it takes a bit longer to execute them. So we decided not to enter the 2-seater class at the current moment. We think that the current 2-seaters on the market are extremely good products, and we think that the market is at this moment, I think there is enough producers for 2-seaters at this market for us to enter. However, we are looking into entering the 2-seater market not before 5 years, but in about 5 years, we will consider that. What we would like to do is that we offer something in the 2-seater market that would be considered as an improvement. And if we're just going to match the current 2-seater designs, we will not enter it. So we will not consider to enter it if there's not a real improvement. And it could be in terms of handling or performance or comfort. We think that the 2-seater market is more aimed for the older pilots. I can also see myself, I start to enjoy flying 2-seaters a little bit more and more. And as you're getting older, especially when you get to an age where you have to fly with a co-pilot is critical. And therefore, I think the emphasis on safety and comfort plays a little bit higher role than what we use in our current design philosophy. So therefore, we will consider the comfort may increase significantly up that ladder. So this is our plan. So not before 5 years, but it is definitely on the cards.
Satisfies or not? I don't know. Don't, any questions?
Yeah, I couldn't hear you that properly, Eva, so just so you know. And there are also some questions coming in, especially from several students. They are asking if there's any opportunities to work for you as either an intern or as an employee. Is that possible if they have the right qualifications, and how should they contact you?
If they're not afraid to work hard, there's always possibilities. We are a little bit skeptical about students visiting Africa and think that they're going to play in the jungle all day and run away from lions. But actually, when they come here, they have to work hard. So we've been, a lot of students has worked for us. And I think we were, in certain cases, having real good contribution from students. And I think we've contributed into their lives also as well. So students with a real desire to improve in their knowledge in sailplane design and would like to contribute, I think we can help them. We've sometimes when products are too busy, we don't have time to guide students. To guide a student, you cannot just give a student something to design and he's successful. You need a lot of guidance, and they need to understand that. And when the pressure is very high on, we cannot always help them. But so far, I think in our life, we've probably helped overseas students probably about 30 or 40, maybe more, which don't work with us. And I think there's another 3 this year coming already. So we always try to help them, but we cannot help everybody.
Well, I think that's good news for some people, and I must urge them to try. And I think you can find the contact details on the Jonker Sailplanes website. And I think we have time for one final question, and that is a question from Adriaan. He's wondering how much time is put into a prototype and how much time is put into a final product, as in man-hour time. For instance, is this comparable to other airplanes, or is there a difference between sailplanes and smaller aircraft?
I don't know what the times for the other aircraft are. I know that the German manufacturers are claiming about between 1,500 and 2,000 hours to build a sailplane. We find that hours too little. We are more in 3,500 hours where we construct a sailplane. But we must also take into account that we don't subcontract anything. So we're doing everything in-house. Well, I said we almost don't subcontract anything. And we are actually building a lot of parts that other manufacturers are buying as third from third OEMs. So you will see the value that we add to our product is maybe a little bit more than the other manufacturers. Although we have some serious plans now to reduce these hours. It is just a careful process to reduce it from so that you don't lose your quality. So if you reduce your man hour per product, there's always a risk of having quality problems. To design a sailplane, a proper sailplane takes around 40,000 man hours to design and to build a prototype. And I think if you do it, the more, as we call it, Lego blocks you have, the less time it is. What I mean with Lego blocks, if you don't have to redesign a wing, if you can just take a fuselage and then you plug other parts on, then it takes much shorter. So we're now in the process to develop these Lego blocks. So I think our Lego blocks that we have is the jet system is possible to drop it in any of our fuselages. The self-launcher system will be possible to drop into our larger fuselages. And then our fuselage that we've developed for the JS2 will be the JS2 recreational self-launcher, as well as the JS5 open class one. We share, for example, the tailplane between the JS3 rest, the rear electrical self-launcher, and the JS4 is the sail tailplane. So slowly we start to have these Lego blocks. And once you have a full packet of Lego blocks available, then the design time obviously comes down significantly. If I may answer, I think I have a few other questions that people is also asking that I can quickly just answer. I think one was about the cost of sailplanes and could it be cheaper? Maybe I'll just explain our philosophy on that. It is really expensive if you would like to design a sailplane. And the customer's expectations and the customer, as I say, the voice of the customer is pushing the aircraft into a level where a lot of design work is required. So to design a new product, to certify it, and to put it in the hands of a customer is really expensive. But it is not the end of the world. The nice thing is that in the glider community, there's a lot of what I call first buyers, and those are people with the financial ability to actually make to support manufacture with new products. And this is a critical part of gliding. If we would like gliding to survive in the long run, we need to inject consistently new products into the market. Why is this required? Because gliders are getting older, getting scrapped, crashed, and so the gliding, the number of gliders is getting less, and this must be filled up with new products. And if you have customers with the financial ability to make the first purchase, it keeps glider manufacturers going. Imagine there's no competition and there's only one sailplane on the market, one 18-meter class sailplane. Everybody will have this. There will be no incentive for a manufacturer to develop a new product. He will only design his latest ABC 5 glider, and everybody will have it. finally nobody will buy new ones. There will be no motivation for new ones, and there will be no sales. So the glider manufacturer will be gone within 10 years. The glider manufacturer will not exist any longer. So we need customers with sufficient budget to buy new gliders. These gliders must get a little bit older and must pass it on to the next generation. Their gliders must be passed over to the next generation, and finally you get your LS4s and your Cirruses into the entry level. And these gliders actually needs to be looked after. So if somebody wants to have gliding more affordable, we really need to look into models that we can revive and keep the old gliders flyable. In our personal fleet, we still have a Cirrus in our company's fleet. We have a LS4. We have these cheap gliders that's actually costing nothing for guys to come and fly and start to fly with. But the top end gliders is not affordable when you enter the market. But it means that the new expensive glider does not kill the market. It actually stimulates the market and makes it possible that gliding doesn't distinct over the next few years. So this is my honest opinion. I'm not sure if am I right, but I thought about it, and I think an expensive glider will not kill gliding. If we stop manufacturing gliders, it will kill gliding.
Thank you, Uys, for your presentation and for answering the questions. I would now like to give the stage to Loris, if Leanne has made him host, and I think she has. So if Loris can come forward, I would like to give the stage to him, and he can start his presentation.
Yep. Hi, everyone. Can you hear me okay and see my screen?
Yeah, we can.
Okay, cool. Excellent. Yeah, hi. So first of all, thank you very much for having me. Very excited to give this presentation. I have to say, I feel a bit the pressure after two excellent presentations, but I feel it's a nice transition from Luke's presentation and the Nixus, because it turns out that Jim Payne, the chief pilot for the Perlan project, is also a test pilot on the Nixus glider. So I'll start by introducing myself very briefly. So I'm Loris Gliner. I've been with the Perlan project since 2016. I joined as an engineering intern whilst I was studying aeronautical engineering at Imperial College in London, and now I'm an engineer, and so it's all a volunteer team. And then my other day job is with Universal Hydrogen in California, where I work on developing hydrogen-powered regional aircraft. So before going into my presentation, I'll start with a short video of the Perlan. Let's see if I can share. Okay, so that was a brief overview of what the a mission of the Perlan 2 looks like. And now during this talk, I'll go more into where the project came from, talk about the glider and its systems, and then what the mission looks like in more details. So first, how did this idea of flying a glider, an aircraft without an engine to 90,000 feet come about? And so the vision really started with Einar Enevoldsen, which sadly left us 2 weeks ago. But Einar was a test pilot for NASA, and on a trip to Scandinavia, he came across this LiDAR image that you can see on the right of the upper layers of the atmosphere, and you see the red and yellow patches show lift. So rising air at 23 kilometers, which is over 70 to 80,000 feet. And so when he saw this LiDAR image, he realized that you could fly an aircraft without an engine to these heights by using those strong air currents. And so he did some more research, and he found out that there were this weather phenomena called stratospheric mountain waves, which would extend, all the way to the stratosphere up to 100,000 feet, that could be used to soar a glider. And so, to prove his theory, he teamed up with the adventurer and the explorer Steve Fossett. And on August 29, 2006, they flew a modified DG505 glider to 50,722 feet. And at the time, they set a new altitude record for a glider. And on that day, they could have actually gone, much higher. So when they reached the peak of their flight at just over 50,000 feet, they were still in strong rising air. But they decided to come down because the pressure suits that they were wearing, they expanded quite a bit, and so the glider became hard to control. And so on the way down, they decided that to go even higher, they would have to build a completely new glider, which would be pressurized so that they can fly it without pressure suits, and then they would be able to go even higher. And that's how the Perlan Mission 2 was born. So now to go a bit more into the goals of the Perlan Mission 2. So the first goal, is aeronautical exploration, and as I mentioned, the goal is to fly to 90,000 feet, which would beat the altitude record from the SR-71 Blackbird, which currently stands at just over 85,000 feet. And this means that when we manage to fly to 90,000 feet, this would be the highest flight supported by its wing by any powered or unpowered engine. And at 90,000 feet, that's the altitude which is more than twice the altitude that airliners usually cruise at, and the air density is only 2% of what it is at sea level, and so it is equivalent to flying in Mars's atmosphere. The second goal of the project is really to do atmospheric and scientific research into the mountain waves and stratospheric and the polar vortex. And so the Perlan glider is instrumented with instruments such as ozone measurements, temperature measurements, humidity measurements, and we can make these measurements and feed them back to weather models and learn a lot more about the polar vortex, stratospheric mountain waves. And this this is crucial to help us understand weather phenomena, because it's believed that the polar vortex into which the Perlan Glider 2 flies has a major role in the ozone depletion mechanism. And finally, last but not least, the third goal of the Perlan Mission 2 is to inspire the future generation of scientists, pilots, and engineers, and for this, an example of this is the partnership that we have with an organization called Teachers in Space, where we organize a competition for school students, but also university students to design CubeSats, which are small cubes of 10 centimeters by 10 centimeters by 10 centimeters, which we then put into the science bay of the glider, and we fly to stratospheric altitudes to perform the experiments. So these are the goals of the mission, but how exactly is it possible to go this high without an engine? And the answer is thanks to a combination of mountain waves and the polar vortex. So, I'm sure many of you know, but that mountain waves can form on the downwind side of the mountain range when there are strong winds across a mountain range. And these winds, when they bounce against the mountain, they create regions of lift and sink, which you can use to gain altitude. It's a bit analogous to surfing in the sky. But these tropospheric mountain waves by themselves are not enough, because they usually stop at the tropopause at around 35,000 feet, and that's your altitude limit. So then you need a second ingredient, and that second ingredient is called the polar vortex. So the polar vortex is an extremely strong high altitude wind in the stratosphere, which you see on the right, which happens in the winters at the poles. And you see you have really high winds which can exceed 260 knots, which go around the pole. And this polar vortex can take the mountain waves and the troposphere and extend them all the way to the stratosphere, creating a phenomenon called the stratospheric mountain waves. And these stratospheric mountain waves can extend as high as 140,000 feet. And so, consequently, these stratospheric mountain waves can only occur at the in the most extreme latitudes. And so this is why all the Perlan Mission 2 flights and missions are done in El Calafate in South Patagonia, where the westerly winds from the Pacific Ocean bounce against the Andes, and then they can propagate to the stratosphere using the polar vortex from the South Pole. And this is one of the only places in the world where you can find those mountain waves. The other place could be really northern Scandinavia. And El Calafate, I should mention also, it's if you don't go there for the stratospheric mountain waves, you should definitely put it on your bucket list for traveling, because it's a really beautiful place with a lot of glacier and the Andes range, which is extremely beautiful. So now let's talk a bit about the Perlan 2 glider itself. So the Perlan 2 glider is a custom-built glider designed by Windward Performance in Oregon. And to this day, there's only one built, and it's completely custom fuselage and wings. And to be as light as possible, it's made entirely of carbon composites. And it has an empty weight of about 1,200 pounds, gross weight of 1,800 pounds, which allows to carry 2 crew members, as well as all our payload for science and atmospheric research. And so, this is comparable to a big glider. And so now let's talk about, the key features of the glider, which makes it different. So one of the main distinctive features of the Perlan 2 is the wings, which are really optimized for high altitude flight. So the glider has a wingspan of 84 feet, which I think is about 26 meters. So that's comparable to, again, big gliders. But the main difference here is that the airfoil section is optimized for very high altitude. So the airfoil is optimized for 60,000 feet. And then another feature of the wing is that the wing is designed for minimum sink rather than best lift to drag or cross country. Because what's interesting for us is really altitude gain, and so our optimization variable for the wing is minimum sink. And in terms of performance, it's at sea level, estimated drag ratio is about 40, which compared to the racing gliders is not super high, but it's really optimized for the high altitudes, and at those high altitudes it has a complete performance which is unmatched by any other glider. And here you can see the flight envelope of the Perlan 2 glider. So at sea level, the Perlan 2 stalls at 37 knots, but at 90,000 feet, where the air is much thinner, so the atmosphere is the density is 2% of what it is at sea level. The true stall speed, which you can see by the blue line here, is over 200 knots true airspeed, which gives a Mach number at that altitude of 0.6. And so also that's why the ceiling of the glider is 90,000 feet, because if you were going to go above without stalling, then your Mach number would increase so much that you would have to start transonic and supersonic effects on the wing, and you'd have to put and so you're talking about compressible supersonic aerodynamics, and you have to have swept wings. If you were to design a Perlan 3, which can go even higher, it would probably have to have swept wings in order to go higher. And then the other interesting thing you can see from this flight envelope here is that at 90,000 feet, again, the difference between the stall speed and VNE, so never exceeds speed, in indicated is only 17 knots. So you get here, it's called the coffin corner, because your margin between your stall and your never exceeds speed is only 17 knots. So that's you have to be careful when flying the glider. Another distinctive feature of the Perlan 2 is the fact that it's pressurized. So following the learnings from Perlan 1 mission, having a pressurized system allows the crew to go to very high altitude without having to wear bulky spacesuits, which would hinder their ability to fly the glider at those high altitudes. So the cabin of the Perlan 2 is pressurized to give a cabin atmosphere equal to flight at around 14,000 feet. And because there's no engine, right, it's a glider to provide the compressed bleed air for the cabin. The pressurized air comes from a scuba tank, which is stored in the aft of the fuselage. And at 90,000 feet, this gives a pressure differential close to 8.5 pounds per square inch. And this high pressure differential between the outside and the inside of the cabin and the outside of the cabin is the reason why you can't have a regular canopy like other gliders, but you can only have small windows for structural reason. And so one of the downsides of this is that it significantly reduces the visibility for the pilots. And to mitigate this effect, there is a camera on the tail of the glider, which you can see on this picture, and this is displayed inside the cockpit. Another thing to note here is that these small windows at those high altitudes where it's very cold, they also tend to freeze because of the bit of moisture inside the cabin. So it's really a challenge for the pilots. Visibility is a challenge for the pilots, and one of them described it to me as saying flying the Perlan 2 is a bit like driving on ice, but with the windshield frozen. So it can be hard at times. Then another distinctive feature of the glider is the rebreather system. And much like in a fighter jet, the rebreather system is an independent closed loop system, which supplies 100% pure oxygen for the pilots. And there's there are two main reasons why we use rebreathers for the Perlan project. So the first one is that it allows to avoid recycling air in the cabin during flight, as the pilots consume oxygen inside the air. So in other words, right, if we don't have the rebreathers, the pilots would consume oxygen which is in the cabin, and the oxygen level in the cabin would go down, and so you'd have to refresh the air inside the cabin much more often, which would require a much bigger air tank, and as a result, a heavier glider. And then the second reason for having rebreathers is that in case of an emergency, so say a depressurization of the cabin, then the pilots still can have oxygen through their rebreathers. Another distinctive feature again of the Perlan glider is the flutter system, which we use to expand the flight envelope of the glider. So as discussed earlier, the Perlan 2 glider is and will continue to operate very close to the boundaries of its flight envelope, especially at the higher altitudes. And these are also flight conditions that have never been experienced by similar aircraft. So there have been extensive ground vibration tests and computer predictions regarding flutter, but to expand the envelope and make sure that safety is our priority, we actually perform more tests every time we expand the envelope at new altitudes to make sure that the response of the glider matches the ground vibration tests and the computer predictions. So as you can see on the picture on the right, every time the glider reaches a new altitude or increases its airspeed for this given altitude, we perform full test points with flutter to validate the moles and before expanding the envelope. And the flutter system, I'll explain briefly how it works. So we have oscillating masses in the spar of the glider, or as well as in the tail. And so you can see, I'm not sure you can see this video, but those masses oscillate around the spar, and then we have accelerometers. So they introduce vibration onto the aircraft, and then we have accelerometers placed all around the airframe that measure those induced vibrations and check whether they are damped as predicted or not. And so this test is performed in flight, and then the readings from the accelerometers are transmitted directly to the ground via telemetry and analyzed on the go. And this is crucial for us because it allows us to clear multiple test points during one flight. So let's say this is the first flight, we go to 60,000 feet. Then we can do the test points at 60,000 feet, and then have the results of the analysis directly, and then move on and go up to 70,000 feet. And it's very important for us because it means that we don't have, every time we reach a new altitude level, it means that we don't have to come down and land and analyze the results, because the number of days, the number of opportunities where you can, the weather conditions are aligned to do those very high flights are limited. And so being able to clear multiple test points on the same flight is crucial for us. Then another key feature of the Perlan glider is its telemetry system. So we like to joke that it's probably one of the most instrumented gliders that ever existed, because all of the systems that I mentioned previously, it generates a lot of data which must be monitored and recorded during the flight. And so this data recording and monitoring, it's done on board the glider. So we have a custom display, which you can see on the right of the picture here, for the pilots to read the data on the air, on the oxygen, on the cabin pressure, on the accelerometer data for the flutter, but also this data is transmitted to the ground in real time. So we have two telemetry channels, one VHF and one UHF. And this data is monitored by a ground crew, which we call Capcom or mission control, to assist the pilots during flights to check that everything is fine. And the other role of mission control as well is they look at the weather models and they give indications to the pilots on where to fly to find the best lift. Also, this another use of the telemetry data is during the flights, we publish some of it online on a website called the Virtual Cockpit, which means that user around the world can follow flights of the Perlan in real time and see live a mission with us and to see how high we can go. And then a final key feature of the Perlan 2 glider is its parachutes. And so the Perlan 2 has two parachutes. The first one, it's located in the tail and it's a drogue chute. And so it's meant to be deployed in case of an emergency above 30,000 feet. And its purpose is to stabilize the glider, but to allow very, very rapid descent and go at the highest possible descent rate. Because if you have a problem at the high altitude or above the Armstrong limit, so you have depressurization, then your number one priority is to get the pilots back down to a safe altitude where if the cabin is unpressurized, they can breathe the air normally. And then there's a second parachute, which can be deployed below 30,000 feet, which is located behind the aft pressure bulkhead, and it's much larger than the drogue chute. And that's really its purpose is to slow the glider down so that you can have a smooth touchdown in case of emergency landing. So that was a brief presentation of the Perlan 2 glider and its systems, which makes it a unique glider. Now I'll talk a bit more about typical mission. So I want to caveat this by saying that every mission every flight is unique, and what I'm saying is roughly guidelines, but generally this is what a mission would look like. And so a flight would probably start the day before, where the team would start preparing the glider, and so it's a bit more complex than preparing a conventional glider. So you have to fill the air bottle for the pressurization, the oxygen tanks for the rebreather systems, install the rebreathers, and perform detailed checks on all the systems on board. Then the next steps, it takes place early in the morning of the flight, so usually very, very early in the morning, where we launch weather balloons about 60 kilometers upwind or on the airport. And these weather balloons, they carry radiosondes, which collect data about the atmosphere. So as you can see, we can generate this QT log P graph, so we can collect data about the atmospheric temperature, pressure, the humidity, the wind speed. And these weather balloons, they can go very high, so that they usually go above 100,000 feet. And they also can travel very long distances. And it's when the polar vortex is very strong, it's not rare for the weather balloons to cross the whole of Argentina and land in the Atlantic Ocean in the east. And so the data collected by the weather balloons is sent directly to the ground in El Calafate, where it's analyzed by the meteorologic team to get information and real data about the atmosphere on that day. And then about 2 hours before flight, there is a weather briefing, and the purpose of the weather briefing is really twofold. So the first objective of the weather briefing is to determine whether the mission is flyable or not. So, in other words, it's like a normal weather for flight, normal briefing for normal flight operations, where you look at the forecast and the balloon observations to determine whether the winds and the clouds are within acceptable limits, and if you'll be able to take off and land safely. And then the second objective of the weather briefing is to identify where there are mountain waves and stratospheric mountain waves in order to determine the best strategy for the flight. And so to help with this task, the Perlan project has two meteorological services partners. So there's Weather Extreme and SkySight. Some of you might know. And we run a WRF WRF model to predict where the mountain waves might occur. And so the results of these mountain wave forecasts look a bit like the picture you can see here, where the areas in red are the regions where there's mountain waves and lift, and then the areas in blue is where you have the corresponding sink. And so here you can see the lower wave, which is the normal mountain wave, and then the higher waves are the stratospheric mountain wave, which extend all the way above 100,000 feet. And this is also a picture of the SkySight model, which does similar calculations. And the pilots also have access to the SkySight model inside the glider, and so they can direct the glider into the best zones to fly in. 1 hour before launch, we would have a flight briefing with everyone included. So that's the air traffic control in Argentina, because we need special permits to fly this high. You have the meteorologic team, the ground crew, mission control, and really you go for over the day's test plan and strategy. And then about half an hour before takeoff, you perform the final checks, and the pilots board the glider. So we do extensive ground tests before the flight. We check the pressurization, pressurize the capsule, and then depressurize the fuselage, and then take off. Which I guess I'll talk a bit about the tow planes, which is also an interesting thing about the Perlan mission too. So for the 2016 and 2017 campaigns, the Perlan 2 was towed to about 10,000 feet by regular tow plane to the low altitude regular mountain waves, and then the crew had to climb this regular mountain wave all the way to the top, and then transition to a stratospheric wave in order to reach the high altitudes. And so this is what they did, for Perlan Mission 1, and also in 2017, when the Perlan Mission 2 set its first record, which at the time was 52,000 feet GPS altitude. But for the last two campaigns, so 2018 and 2019, we have done things slightly differently, and we've been using a Grob Egret as our tow plane. So the Grob Egret was originally designed to be a German high altitude spy plane, but we've converted that to a tow plane, and now we can tow the Perlan to over 40,000 feet directly. And so this allows us to tow directly into the stratospheric mountain wave. And this is very beneficial for the team for two main reasons. The first reason is that the number of days where that low or tropospheric low altitude mountain wave overlaps with the stratospheric mountain wave, so the days where you can make that transition from the lower wave to the upper waves, are quite limited. So the The days where the weather conditions align for that are, there are a few of them. And so towing directly into the stratospheric mountain waves gives us a lot more windows to fly high and perform scientific experiments. And then the second reason is that it takes quite a long time to go from like the 10,000 feet to all the way to the top of the tropospheric mountain waves and then transition. So, on the flight to 52,000 feet we did in 2017, it took about 3 hours, which means that once you're in that stratospheric mountain wave, you have less time to climb and do scientific experiments before you need to go get back on the ground to recharge the batteries, the air, and the oxygen. So towing directly into the stratospheric mountain waves really allows us to maximize the time spent into the stratosphere. And then the final step of the mission is the return to base. So that's just to say that a mission usually lasts between 4 and 6 hours. And so this is my final slide, which is a bit of a project update and next steps. So the first flight of the Perlan 2 took place on the 23rd of September 2015. And since then, we have done 65 flights and organized 4 missions in Argentina. So 2016, 2017, 2018, and 2019. During that span, we broke the world altitude records for gliders 4 times. So first time in 2017 with a flight to 52,000 feet, and then 3 times in 2018 with flight to 63, 75, and then our highest flight on September 2nd, 2018, which was at 76,000 feet pressure altitude. And that 76,000 feet is actually the highest wing-borne subsonic flight, higher than the U2, the American U2 spy plane, which was at 73,700 feet. We went back in 2019 and tried to fly even higher than that. But when we were there in 2019, there was a rare meteorological phenomenon called the sudden stratospheric warming, which decreased the strength of the polar vortex and prevented us, to exceed the 76,000 feet flight. But nevertheless, we made the most of that out of that season, and we had a flight to 65,000 feet, and we spent a lot of time into this stratosphere collecting data about this sudden stratospheric warming and the polar vortex, which will really enable the scientific community to understand more about these sudden stratospheric warming events, because little is known about them. And then due to the COVID-19 pandemic, unfortunately, we couldn't organize a campaign for 2020, and we won't be able to organize a campaign for 2021. But in the background, the team has been really busy analyzing all the data that we have collected, making improvements to the glider, and we're currently planning a campaign for 2022. So stay tuned for that. All right, I think that's the end. So I'll be happy to answer any questions.
Thank you for your presentation, Loris. Before we get into questions, we will get into the questions. We wanted to thank you all. I hope you can see my screen now. We wanted to thank you, Uys, Loek, and Loris, for giving your presentations. I enjoyed them very much, and I hope the audience did as well. Because it is our Lustrum, we have organized or we have arranged some merchandise to come into our association, and we would like to thank you by handing you over this tie and the mask according to our theme, Time Flies. So you will receive those hopefully sometime soon. We will contact you about how we will send them to you. Then indeed we would like to get into the final questions. So first we will indeed ask some questions to you personally, Loris, and then we will well, look at some more questions to other speakers as well. So Tim?
Yes, thank you all for your presentations. So first of all, I would actually like to start if any of the speakers have questions to other speakers. Then afterwards we can have some time for some questions to Loris. And then we want to open up the discussion a little bit more and give people some time to ask questions for themselves. So slowly we will allow more people to use the microphone. But keep posting your questions in the Q&A, please. And yeah, one of the speakers, if you have any questions about any of the presentations, go ahead.
Can I have a question to Loris?
Yep, go ahead.
Just in terms of this high temperature, high altitude flying and the temperatures involved in this flying, did you guys have any special surface treatment, special gel coats or paintwork selected? And did you have experienced any gel coat cracks or something with a change in temperatures? Because this is quite a common problem for normal gliders, that they don't like these altitude and temperature changes.
Yeah, that's a good question. And so yeah, so the temperature at, you know, when we get to the stratosphere, we've seen minus 60 degrees Celsius, so it's extremely cold, and we've had a lot of issues with temperature for the electronics and, you know, keeping everything warm. And as for the paint, the paint of because the Perlan Mission 2 is sponsored by Airbus, the paint of the glider is actually the same paint that you would find on the Airbus airliner.
Okay, but was there any gel coat layer, or is it just paint directly on top of the composite substrate?
You know, that's a good question, and I don't know off the top of my head, but I'd be happy to you know, to ask the team and get back to you on that.
Okay, thanks. Interesting.
Well, it's nice to see that people can learn from each other, even if they have that's so much knowledge as that you have. So for a question to you, Loris, if I can scroll up. So what do you think that are the main feats that you had and what you learned from it, which could be applied to other fields for such as commercial aircraft design?
Yeah, so it's a great question, and I think, you know, there are a couple of things there. So on the aerodynamic side, I think we're learning a lot on flying at the higher altitudes and in very low densities, and I think that's very relevant as we saw a couple of weeks ago, the first Paris flight on Mars. And so flying to these high altitudes is actually very similar than the atmospheric conditions of Mars, so we can learn a lot there. And then with all the data that we're collecting, there's also a lot of learnings that can be derived from there. And so, you know, there's very little known about stratospheric mountain waves and the polar vortex, but meteorologists believe that that they have a major impact on, you know, the ozone depletion, as well as they affect weather phenomenon greatly around the world. So being able to model them accurately in the weather models would greatly help improving the accuracy of these models. And so the Perlan 2 is a really good platform to collect data about these stratospheric mountain waves in the polar vortex. And, you know, it's very good because it's able to keep station inside that wave. So if you send a weather balloon, it will only cross that wave, but then it will be pushed by the wind out that way very fast. Whereas with the Perlan, you can keep station in a particular area and collect the data that you need there.
Ah, cool, nice. Yeah, I can imagine that those are valuable insights. So about those stratospheric waves, mountain waves. So can you also find them in the northern hemisphere? And is the polar vortex there also present? And is that usable or not?
Yep, exactly. So, you know, Einar, the first LiDAR image he saw of the stratospheric mountain waves were actually in northern Scandinavia, so in the North Pole. And so the polar vortex only happens in the winter of that pole. So in, you know, the June, July, August timeframe for the South Pole in Argentina, and our winter for Scandinavia, so, you know, December, January. But and you know, this is something we've looked at. You could potentially do similar flights in the northern hemisphere too.
That's nice. So what I would suggest is that if someone has a question, you could say that you want to ask your question personally in the chat, and if you do, you will have the option to unmute yourself. But if you would like to wait for your turn and not disturb anyone else, just as well when you're transmitting on the radio while gliding. And in the meantime, I will ask one final question. So I can imagine that for the test pilots, it's really difficult and really new experience to fly in the Perlan project, right? So how did they do their training? Did they do that in flight simulators beforehand, or did they take it up a notch at every flight?
So we do have a flight simulator, and also, you know, the pilots are extremely experienced. So our chief test pilot is Jim Payne, who, you know, also flies in Nixus, but he's had a very long and distinguished career in the Air Force, where he was, you know, a test pilot for the Air Force, and he flew, you know, also I think gliders to 40,000 feet before. So he's probably one of the best pilots in the world, and so that's, you know, that's how he trained for that. And then, you know, we also have 3 other pilots who fly in the back. So that's Tim Garner, Morgan Sandecock, and Miguel Iturramendi. And so, you know, they all have extensive gliding experience. You know, Miguel is an experimental test pilot. He's probably flown over 20 aircraft. So you know, you can't really train for that because it's the only aircraft of its kind doing this. But with simulation and other experience, that's how they can prepare as best as they can.
Cool, that's nice. So I don't know if anyone yet wants to ask a question from the audience. So I will pause for 10 seconds and wait for someone, and otherwise I will continue. So I guess that's a no. So a question that is posed in advance a number of times was if the Perlan project eventually will take passengers with them as well.
That's a good question. I don't think it's part of the plans right now, and really because it's not a pilot and a passenger seat. It's really 2 pilots on board, and both of them are critical to ensure the safety of the flight. So you can't take a passenger to go sightseeing inside the stratosphere, or we'd have to do a 3-seat glider. But you know, if the crew has enough experience, then who knows, everything's possible.
That's cool. I think people will be overjoyed to hear that. So
well, it's not enough for for the moment. It's really the 4 pilots for now.
Yeah, it will be very late very far in the future, of course. So maybe to mix up the questions a little bit, I will pose a different question. So maybe one of you, Uys or Loek, can also answer this question is, what do you think that the limit will be for normal commercial gliders for in terms of glide ratio, so in the near future?
Maybe Luke will be better to answer this question. So we can just say what we are thinking. We don't think that L/D is any longer a critical design parameter. So we are thinking more about designing aircraft to have an overall performance of climbing well and cruising well. The number of times where you're actually using best L/D is normally not making sense anymore. So even if we cruise in the worst of conditions, we're nowadays flying at 160 kilometers an hour. At 160 kilometers an hour, you may be 1 or 2 points below the best L/D, but you do that at 30, 40 kilometers an hour, maybe 50 kilometers an hour faster than the best L/D. So we never fly best L/D. So the critical design parameters, if you would like to have a maximum performing sailplane, is to climb well and to be able to climb at quite a tight circle. So this is important for small thermals. And then to climb well to cruise well between 180 kilometers an hour and 200 kilometers an hour. And if you fly for records, even to fly well at about up to 240 kilometers an hour. But to answer your question, the best L/D is depending on aspect ratio and wingspan. And if you make a rule of thumb, you can almost say the theoretical maximum is double your aspect ratio or 3 times your wingspan. But this is just rule of thumb. This is what one can think where you can get. So for open class, we think you can reach in the 70s, like Luke has explained. In the 18 meter, we figured out that you can reach about 58, and in 15 meter you can reach about 50. So this is what we think one can achieve. It's funny enough that it seems that you can get a little bit more out of 15 meter than wingspan times 3 or aspect ratio times 2. This is our experience. Where you can get, I would like to ask Dr. Bosman, what is your feeling? Maximum probably about 72, 74 in open class, which Luke is also predicting.
Maybe Luke wants to respond.
Yeah. If you want to have low sink rate at low speed and also good performance at high speed, then usually in between it is something in between. Unless you really focus on 2 or 3 flight speeds to be the best in those conditions. So it is quite normal, or just not so bad, to have the best L/D as a measure of overall performance, although you don't use it. That's true. My guess is, well, I am careful because when I was younger, then Professor Boermans thought that the end of the development of the Air Force was nearby. But since then, we managed, nevertheless, to make nice improvements. So I don't dare to say that we, although I changed over to boundary layer suction, because it is really very, very difficult to squeeze more out of the Air Force. But who knows? Somebody with clever ideas, you don't know.
Yeah, maybe they are sitting among us right now, those clever ideas.
Yeah.
So,
if I may, I would like to stress another thing. There was one man in the questions posed before, Eco Boy. He has 2 questions about the low-cost glider. Could TU students define specifications for low-cost glider as a research project? I will stress that in Germany, I worked on the design of a very light glider. Even if you manage to get the weight below 120, you don't need the medical in Germany. And it is heavily underestimated to make a good glider in that class, really. I try to do it, and it will go into the air soon. And I hope that it is better. To fill the gap between the hang glider and the light glider is really not easy. So I think the Tijd Vliegt students, one of those clubs should try to come up with a good design. And they will find out that it is very, very difficult. It has to be very light. It will fly very slow. And in order to get some more speed out of it, the lift range should be high. So the lowest lift coefficient, what I could realize is 0.175 and the highest is 1.75. And in those cases with a low wing loading, you do not fly backwards if there is a little bit wind. No, it is reasonable. But it is also much, the flight speeds are much lower and the mass is much lower. That safety precautions, as we are doing now for normal gliders, maybe they are not needed. Because the impact, half mv square, the mass is low, the mass is now less than half of the normal. The speed is about half. So there's 1/8 of the energy has to be destroyed compared to a standard class glider. So then you can pose the question, what safety precautions can you do in these things? Except from that they cost weight, usually. So there's a lot of things to think over in order to make a light plane, which should also be more affordable, cheaper, finally. Maybe it's in the end it is expensive nevertheless, because you have to approve special carbon fiber and so on. Maybe that makes it expensive, but who knows?
Okay, all right.
My message to the Tijd Vliegt is don't underestimate that type of glider. And maybe if you can find out some good glider, it will be very interesting for a lot of people who are just flying around the town and not cross country.
Yeah, exactly.
Just wanted to stay up.
Yeah, true. So before I pose another question, I would like to stress that if people have to leave because we already are over time, please don't be afraid to do so. We always like to thank you for your attendance and also for the speakers. It's the same. And I would like to ask Leanne if she can give speaking permissions to all the question posers in the Q&A. So after my following question, we can try to get some questions from the audience directly. And so I had a question to you, a follow-up question, Uys. So you say that the lift of drag is not that important. And I saw a question on the Q&A which stated that maybe the technology of the Perlan project for the flutter to increase the VNE by using those counter flutter devices can also be applied to gliders to increase the VNE at low altitudes. So both to you, Loris, and to us, do you think that's viable, and do you think that will improve the performance of cross-country gliding?
So maybe just a clarification. So these devices are not counter flutter, but they are devices which induce vibration on the wings, so that we can verify the flutter models that we have on the ground in order to expand our envelope. Okay.
Yeah. Okay. Sorry, that was my misunderstanding. But you do know more about the flutter characteristics than, well, maybe more than other experiments before, right?
Exactly. And so, the big advantage of that is it really allows us to have experimental data rather than models to validate the models. And so, in some other cases, it could perhaps allow you to expand the envelope of your glider if it turns out that your models are slightly conservative.
maybe I can add some piece of information that is maybe not so commonly known, is that your range where you have to demonstrate that your aircraft is flutter free is dependent on a formula in the CS22 that is based on your wing loading. So the higher your wing loading is, the higher the stall speed is, and therefore the higher the VD, that is your design speed is. So an aircraft must be flutter free up to VD, and you must demonstrate it up to VDF, which is about 10% less than your VD. If you select it, you may select it 10% less. For a high wing loading like a JS3, which is about a 60 wing loading, your VNE that your VD that you have to demonstrate is up to about 324 kilometers an hour. This is much higher than where the aircraft is efficient to fly. So the aircraft is extremely safe up to speeds we normally fly, and the maximum speed we have flown in contests. Cruising speed is about 240 kilometers an hour in South Africa in one contest, and that is still way below your VD. So by increasing your VD will have no performance benefit on the aircraft as well. There's already a significant safety margin in it. I would say in Europe you rarely fly above 200 kilometers an hour efficiently, and I would say in Africa up to about 240. So having a VD of 324 is really adequate. I don't think any gains are there by increasing that.
All right, that's nice. So, is there anyone from the audience? So I'll give some short time for a question to come up. Doesn't look like it. There are a lot of questions though. So specifically one for Uys, if you're still using the open data from OLC online, for instance, to do some data analysis, and how do you compare the data between the Alps and flatland Holland?
I have to verify first with my aerodynamic expert before I can answer.
We have an entire panel in South Africa.
No, we don't use OLC data. Honestly, what we are using is we're using the EDAFLIC performance data for feedback on our own aircraft, and this is sufficient to push into our models to determine the cross-country models. For cross-country data, we do verify. We're using some theoretical models as we use for the models. As we said, we have this integrated design process, and the weather models is basically, which one is it? Was it from just a simple one from, is it Thomas? Fundamentals of Sailplane Design. So we're using those thermal and weather models. And in the end, we check on contests and hear what top pilots are saying. So the easiest to hear is what the top pilots are saying. If there's a world championships and the aircraft are performing against one another, you immediately know what your aircraft is doing, where it's good and where it's not so good.
Yeah, I believe that Loek also uses the experiences from top pilots, right?
Yes, but what is probably more important is that these cross-country speeds calculations are built up of a model where you glide and climb, and your starting altitude is the same as your end altitude. But that is not what happens in practice. If the pilot encounters low climb speed, they stop climbing earlier, and when they encounter high climb speeds, they climb more to a higher altitude to take advantage of it. I let 6 pilots fly and we around in the Netherlands in the same period of time, and analyze their log files, and then you can see what they are doing. And that's exactly what I say. They stop earlier in at low climb speed, and they climb further on at high. And if you take that into account, there's nearly a parabolic curve where you can plot through these points. If you do that, then your final cross-country speed is higher than what is calculated in this so-called McCready theory. And that was long time, but that was how can that be? Then in practice they are faster. Apart from that, they take during the glide, they take advantage of cloud streets or whatever. Then they easily take LOD of 100. But that was not the problem. You can implement that in the theory of McCready as well. But this factor that they stop earlier or climb further on increases the cross-country speed, and that comes more close to reality. We are not still there, but and that's what I do.
Yeah, I agree with Luke there. So the pilots are not flying statistically what you would expect from a model. So they don't fly blind eye. So they're following the weather patterns, and the performance that they squeeze out of the aircraft are sometimes amazing. You cannot believe what on paper. Therefore, it's quite difficult to use OLC models because, as Lucas said, is the pilots are making modifications to optimize the weather available to them, and it is much higher than a theoretical model, which will statistically evenly provide lift and sink lines, or lift and no lift lines.
Yeah.
And Loris, how do you see that? Do you also have some sudden, unexpected surprises that improve the performances of the Perlan project, or don't you have that?
Not sure. So it's the Perlan is really optimized for minimum sink and not lift to drag, and that's why also it's got we don't even need a retractable undercarriage because the aerodynamic performance in the models is really not what we're looking at. It's a completely different mission with a different set of parameters to look at.
Do you have a non-retractable wheel?
Yeah, it's a non-retractable landing gear, and the reason for that is in order to have a nice pressure vessel for the pressurized cabin. Okay.
All right, and that's nice to hear. And then we have a question from the audience. It's from Sylvain. It's from the Delftsche Studenten Aeroclub. And he would like to ask a question personally. So Sylvain, if you would like to take the floor. We can hear you.
Oh, okay. Okay. Awesome. Cool. So that's a question to you, Uys. Perhaps this question is a little bit too technical for this discussion here, but I hope you can still give some answer. So with respect to the global optimization you have in your aircraft, have you ever done any research on the impact of pilot thermal interaction when passing through a thermal, and what the optimal way would be for a pilot to fly through a thermal? So for example, you have dolphin flying or dynamic soaring. And is there any perspective on optimizing an aircraft, including its handling characteristics, when passing through thermals or gusts?
Quite a good question. So how I understand the question is, what do you do as a pilot to fly through thermals, and how do you react, and what is the best way to do it? Now, this is not so easy to mathematically model it, although you can. But what we have learned from experience is the following. We have actually learned two things. If you fly with a flap glider or unflap glider, first I will just explain how do you deal with your flaps. So what we have seen after we have designed the automatic flap system, so we designed the auto flap system to check what the effect will be, and we base this on your rate of climb and your G inputs, and then your speed, and then the system automatically adjusts the flap. And we were actually quite amazed to watch this flap handle moving forward and back. And this actually learned us how to fly with flaps first. So this is not really your question, but I would like actually to disclose this information because it's quite interesting. So when you fly fast and you're in a negative flap position, and you enter a lift and you pull up, the best way is just to keep in this negative flap as long as possible. So there was no advancement of the flap at all while you're pulling up and while you push over negative and with reduced G. But as soon as the speed is low and then you pull back the stick, then suddenly the flap advances quickly fast backwards into a thermal flap position, which showed us that if you do normal flying, and you're just pulling up and push forward again, you just stay in negative flap. You don't touch the flap lever at all. Because the negative flap makes up for the reduced lift required. And when you accelerate forward, you don't need to change your flap. But whenever you decide that you actually slow down to a level where you're going to not push over and you maintain a low speed, then you have to advance the flap towards the optimum flap position. So it actually advances quite fast to a climbing flap position. And when you then start turning, it immediately advances into the climbing flap position. It was amazing to watch this thing operating, moving forward and back. And then we realized it's so easy to operate flaps that you don't need an auto flap system. It's just too easy to fly. You leave in your cruising flap position, you do your dolphining, and whenever you require that extra bit of lift, only then you advance it forward. The question to pull up or not to pull up is also interesting. Obviously, it depends on your height in the first instance. And the second thing, it depends how long the gust is. If it's only a gust, that is, and I would define a gust, then it's about less than 6 seconds. If it's just 6 seconds, it makes more sense just to cruise through the lift and make horizontal changes to the best lift instead of pulling up. But if the lift is more than around about 6 seconds, and I talk now for a fast flying glider, loaded glider. Obviously, if you fly with a K8, this 6 second rule is much shorter. It could be as low as 2 or 3 seconds. But with a fast glider, it makes more sense to maintain your speed. But if you have a long stretch, if you can see this is a big cloud with long lift, then you actually reduce the speed almost to what I would say your cross-country speed would like to be. So if you plan that your cross-country speed for the day would be 120, it doesn't help so much to reduce the speed much lower than 120. The longer the lift section is, the slower you can slow down to. So it's quite interesting. I think the Polish pilots, which we regard as the best cruisers at this moment in the business, Sebastian Kawa and Zibi, they are flying, maintaining their cruising speeds for quite a long time, and don't slow down and don't pull up aggressively. So we are flying a much more flatter profile nowadays of pulling much slower up and making smaller speed reductions. So we typically cruise at 200 kilometers an hour. And if you encounter lift, you only slow down to about 160. And then you continue again back to 200. If you're at 160 and the thermal keeps increasing, you slow down maybe to 140 and you leave it at 140. And only if you decide it is worth to climb, then you roll into the climb at 140 and just use that last bit and reduce the speed to 120. Because mainly with this normal gliders, the high performance gliders, you don't reduce the speed much more below 120. So to summarize, we don't pull up if it's less than 6 seconds. If it's more than 6 seconds, you advance the speed slowly down. If you decide to climb, you slow down and climb at 120. I'm not sure if that answers the question.
Yes, it does. Thank you very much, because I've done some calculations and made a mathematical model on passing through a thermal, which is just simple with a quadratic lift drag curve. But actually what the program was doing when flying into the sink, it would point the nose up and then point the nose down when encountering an updraft. And in that case, getting dynamic soaring. And only if the thermal is very large, as you just described, then it would also, after that, pull the nose up to fly slow in the updraft. This is incredibly difficult to implement when flying yourself, because you don't know what the updraft or downdraft will be. But yeah, it's an interesting theory, and I have never seen anyone do it. And I was wondering what your perspective is on whether such a thing could work.
I think to gain something out of dynamic flying is I don't think that is so easy. I don't think that anybody has managed it correctly. So for us mortal pilots, the best to do is just not to accelerate too late into the sinking area. So by accelerating into the sink, our experience is that you lose more than you gain if you accelerate a little bit quicker while you're still in the lift. Just that last bit, as soon as you see the lift tapering down, you start your acceleration and don't accelerate in the sink, where the theory of dynamic soaring is to accelerate vertically down into the sink to give yourself more sort of a velocity component, a downwards component with a sink, which is based on reduced drag while you accelerate with gravity down. I haven't seen anybody managing accelerating in sink and gain out of it. So practically, we couldn't simulate that in flight. I think theoretically you can probably do it, but you don't have enough input to know exactly where to accelerate. So what we are doing is you just accelerate as soon as we see the lift is tapering down. We gently accelerate, and that we are close to cruising speed as soon as the sink starts. But it is difficult. This one is a difficult one because the theory and the practical is not really aligning in this instance.
All right. Yeah, thank you very much. Great.
So it's right now it's 11 o'clock. So well, the symposium went on longer than we would have thought. We would like to thank all of you very much for this wonderful event. We had most of the time more than 200 people attending, and right now even more than 100 people attending. So I think that is a very nice event to close this off and have one final chat in the Zoom.